तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to the last part of the lecture series in computer graphics. In the last class, we had discussed aspects about digital image processing, mainly the concept of digital image compression, the JPEG format or JPEG. Towards the end of the last class, we just covered in very brief the concept of digital image enhancement, and we also looked at what is contrast stretching. So, we will start from that where we left off, and we will discuss concepts of digital image enhancement. Okay. This is an important aspect, of course, in digital image processing or digital image manipulation, where you have digital images stored in a certain format. It could be JPEG, TIFF, BMP or whatever it is, and then if the quality of the image which you have obtained, okay, is not very good in the sense that it could be corrupted by noise or due to the sensor effects, that the illumination is not good or well distributed all over the image, you would like to enhance the image quality. So, we will talk about concepts of digital image enhancement, and there are many ways by which you can enhance a digital image, okay, and it will be covered in the course, extensive course on digital image processing. Just to name a few, there are two broad categories of digital image enhancement techniques, one based on spectral or Fourier based filtering techniques as they are called, or based on digital Fourier transforms, which we will not cover here. The other is based on the other category is based on spatial transforms or transformation done on the image pixels itself in the spatial domain. So, we will mainly concentrate on spatial domain analysis, and that too we will talk about mainly three different types of digital image enhancement, one based on contrast stretching, the other is probabilistic distributions, which is based on the image histogram. So, we will understand what is an image histogram, and we will talk of the simple technique of histogram equalization. Histogram equalization to enhance the image, and of course, the third category will also see the concept of filtering an image in the last part. So, let us look into the slide of digital image enhancement, that is the topic under digital image processing, which we will be talking about today. Under digital image enhancement, the first concept is contrast stretching. This is a pixel based operation where a given gray level within the range 0 to L, this value of L depends on the number of bits used to store a gray level value or a pixel value, and that is a variable r lying within this range, and that is mapped onto another gray level S, which also lies in the same range 0 to L according to a transformation function S is equal to T of r. So, depending upon the S equals T of r you choose, you can have different type of enhancements. In fact, you can have de-enhancement also. You can degrade the quality of the image, you can also increase the quality of the image and enhance it or de-enhance it way, that means attenuate in some sense the gray level values depending upon your requirement. Okay. So, S is equal to T of r, r is the variable used for the original gray level value or pixels in the image, and the S is the variable for the transformed values. So, you are transforming values from r to S using the transformation function T of r. So, that is what we have seen here, and what is the main purpose? The process is mainly done, and it basically means it is used to enhance images, and it is mainly done to handle low contrast images occurring due to poor or non-uniform lighting conditions, or due to non-linearity or small dynamic range of the imaging sensor. Okay. So, the image could be degraded due to various reasons. Okay. There could be non-linearity in the imaging sensing device, the dynamic range of the response of the imaging sensors. When light falls on the sensors, the light energy is transformed to electrical energy, then it is converted to a digital value. That is how typically the CCT based sensors or even any other electromagnetic sensor or solar sensors work. Okay. Those sensors may be faulty, or their performance range, dynamic range of output values are not large or wide enough for you to give a high contrast image or a good quality image. Okay. So, in those conditions you apply transformation, S is equal to T of R. Okay. And the last part is we will see an examples, following examples will show typical contrast stretching transformations. We will go through a few examples of very simple contrast stretching transformations, which we will see now. Okay. Let us take this particular example. As you can see, this example we have also used in the last class to demonstrate the concept of image compression using JPEG format, the original image of Lena, and we use a transformation function of nonlinear function of this nature, S equals T of R. S equals T of R. So, R is being transformed to S using this function. Basically what you mean is you pick up a pixel value which could be bright or dark depending upon where you are. You can actually do row wise or column wise scanning, and for at any particular point x comma y on the image, you pick up the gray level value, go to that in the horizontal scale in this S equal to T R function, what is the value of R, find out corresponding to that what is the value of S. Okay. So, if it is higher, it will be you will be getting a higher value of S. If it is low value of R, you may get a low value of S. Now, if you see the what is the purpose of this type of or nature of this transformation function, what it basically does is low values of R are made still lower, pushed down, and higher values of R are pushed to a larger value, and that results into an output image of this nature here. As you can see, the brighter portions have become much bright and darker regions have become very dark. Okay. You can almost guess that if S equal to T R function is a linear function where S is equal to R, okay, with the slope is equal to 1, the output image after contrast stretching will be the same image as the original image if S is equal to R. However, if you use such a transformation function where darker values are made much more darker, brighter values are pushed to the large brighter range, this is what will happen, where you see dark regions will become still darker and brighter regions will become very bright. So, that is an example of contrast stretching here, S equal to T R. Let us take just the inverse effect of this transformation function and see what is the effect. So, go to the next slide. As you can see here, if you take S equals to T R of this nature where darker values of R in the original gray level image are transformed to a high value of S, and brighter or large values of R are transformed to low values of S, this is the output which you will have after contrast stretching. What happens here? As you can see, brighter values, say here or on the top or on a shoulder, they have all become very dark, and darker pixels, you can see here this patch or regions in the here, in her here, they have all become very bright. Okay. So, just it is an equivalent to say that you have actually got a negative of the image in some sense, negative of the image. Of course, a perfect negative image can be obtained when the slope of this, it is linear and S will be a constant minus R, then you would have had a perfect negative image, but this is almost negative like. Okay. You do have very dark pixels and very bright pixels, just the opposite function. If you just look back and compare these two transformation functions and the corresponding output, let us roll back and see. This was what we showed earlier, S equal to T R, brighter pixels become more bright, darker pixels become very dark here, or even you can see the reverse effect is here. As you can see that dark pixels become very bright and bright pixels become very dark here. Okay. So, this is an example of contrast stretching in either directions. You are free to write a small program and take any arbitrary S equal to T R function and observe what is the effect. You can actually have magical effects both in a gray level and a color image. You can experiment yourself and see what is the result of this contrast stretching operations. Now, let us take another example. Okay, let us take another example. As you see here, the original image is given here, and we expose it to a transformation function of this nature, s equal to TR. Now, this is also a nonlinear function. It is basically an exponential curve, in the sense that, of course, is something like a BH characteristics in electromagnetism. And if you provide such a function, transformation function, where you pick up pixel values from this image, find out where it is in the r axis, correspond to that, find out what is the s axis. If you do it for all the pixels in this image, what will be the result? You will get something like this. Okay. As you can see, that the image has not changed much in its quality, but you can see the background. You can see the background here, they have almost become very bright. If your TV quality is good, the medium in which you are observing this, as you can see here, this is an example of what is called as a gamma correction in image processing or even computer graphics. This is an example of a gamma correction. Okay. I will avoid the equations, but you can implement this gamma correction using this transformation function as an example given here, and the gamma is a parameter of the curve. In this case, gamma is less than 1. The lesser the value, the more steeper the curve will be. Okay. Okay. In fact, gamma is equal to 1, the s equal to TR function is a s equal to r example. That means a linear one from left to right, as you can see here. So, this is an example of a gamma which is less than 1. More lesser than 1, it will be more sharper. When gamma is equal to 1, you have s equal to r. Okay. When gamma is more than 1, this is what will be the result of the curve, and the corresponding output, as you can see here. This is definitely much different than the original image. As you can see, it is much darker with this transformation function for gamma greater than 1 here, and the corresponding this output using this transformation function, you have this output, whereas from the original image using this transformation function, you have the transform. So, these are the transformed images obtained by the corresponding s equal to TR transformation functions. Okay. So, these are certain examples of contrast stretching, okay, and by s equal to TR functions. Okay. Now, what this s equal to TR function does is, it does not worry or tell you what the image is in terms of in what sense it is poor. Okay. You are blindly applying s equal to TR function on a darker image or on a brighter image, or you can apply it on a richer contrast image already, and in some cases you may land up with poorer results. So, it is not automatic, or in some sense it does not derive out any information from the image and then adjust the parameters of the curve s equal to TR. So, it does not do that. Okay. So, we need certain enhancement techniques automatically in certain digital image processing applications, where the image should be, if at all, if the contrast is poor, in the sense that it is very dark or things could be very bright, in either sense the images are bad. If the pixels mostly are very dark or very bright, the images in general are not often of good quality. When you say subjectively, of course, that the image is of good quality, you typically have all dynamic ranges of pixels, starting from some pixels which are very dark to some pixels which are very bright. We will see with an example later on just now, but the concept of, or the concept which we are going to discuss right now, talks of an automatic or semi adaptive method by which the information is derived from the image about whether in what way the quality is poor, and then adjust the pixel values using some transformation, adjust the pixel values based on certain transformation. And we are going to study the concept of what is called the histogram equalization based technique for image contrast enhancement, by histogram equalization. So, that is the next slide now. Often we will use in short a HEQ term, which will mean nothing but histogram equalization. So, before going into the concept or algorithm on histogram equalization, we will first understand, we must first understand what is a histogram of an image. Okay. So, what is a histogram of an image? Let us look back into the slide and try to understand. In a gray level image, the probabilities assigned to each gray level can be given by the following relation. Let us introduce these variables and then we will look into the expression, which I am not bringing right now. So, we are talking of the probabilities assigned to each gray level and where r k. So, you remember this r variable was there, now it is that k subscript has come which talks of discretized values of r, the normalized intensity value r k, and L be the number of gray levels. This variable is also not new to us. These two are new variables. N k is the total number of pixels or the number of pixels with gray level value r k. Now, r k could run from 1, 2, 3 and so on. So, for a certain value of k, k is an integer and we have a gray level value r k, and for that the image has n k number of pixels. That is the most important part. So, you have to basically count how many pixels you have in the image, the number, count the number of pixels in the image which have the gray level value r k. Okay. So, that is the value n k here. So, as you can see here, n k being the number of pixels with gray level value r k, and of course, small n is the total number of pixels. So, summation of all these n k will be n, we will see that there is a total number of pixels in the entire image. So, if I have understood these 4 variables here, this is the expression of what we mean by the probabilities assigned to each gray level value. PR of r k is given by n k by n. You know what is this n k? N k is the number of pixels with gray level value r k, and the denominator is the n, which is the total number of pixels. So, this probability value, it will be less than 1, it will be running between 0 to 1, okay. N k maximum can be 1 at the most, and the r k values we will say normalized intensity value. So, it runs in the range 0 to 1, r k values normalized range runs from 0 to 1. Remember, k is an index. So, it must be integers running from 0, 1 to L minus 1, because if L is the number of gray levels in the image as given here, L is the number of gray levels in the image, k runs from 0 to L minus 1. So, there are L different levels and the level runs in the normalized range 0 to 1, because it is just normalized range. So, these are fractional values r k, and for a certain value r k given an index k, n k is the number of pixels with that corresponding value r k divided by the total number will give you the probability that so many number of pixels will have a value r k. So, the plot of this PR of r k versus r k is nothing but is actually the histogram of the image. So, let us look at an example of the image. This is a typical case of an example of an image, of a satellite image. The histogram of the image here is given below. So, if you look at this plot, on the bottom of the x axis you have the gray level values r k. Of course, I must admit here that the value is not normalized, it runs from 0 to about 256, and there is a horizontal band of intensities as you can see here, which is running from very dark to bright values. So, the darker values are from 0 to about 100 and brighter values are from about 150 to 256, the maximum values. So, if you divide this range by the maximum value 256, which is L, and the number of gray level values, then of course, you will get normalized range r k 0 to 1, and the vertical coordinates this display the n k number of pixels with gray level value r k. So, it is basically a plot of n k versus r k unnormalized. I will say in this case the probability to normalize both the axes, you have to divide the vertical values on the vertical axis by n and on the horizontal axis by a value L, otherwise this is a histogram value of n k versus r k unnormalized. So, that is a histogram example which says that at what is the count or number of pixels which exist in this image with a certain gray level value. So, you can see that there are almost negligible amount of pixels with very low, very dark pixels and few brighter one, most of them is somewhere in the middle. So, the image is of moderate quality, almost we can infer by looking at the histogram that the image quality is not bad, because the almost all the entire dynamic range of the pixel values are covered, and we will see that this image in general does not require enhancement, but just to understand what is the histogram, that is the example. So, the plot of PR of r k with respect to r k is called the histogram of the image, that is the definition of the histogram. So, in this case of course, I must inform you that we are plotting NK versus RK unnormalized range, but you can easily transform this to a normalized value. So, that is the histogram. Okay. So, let us look at some more examples of images and their histograms. As you can see here, for this image, this is a image borrowed from, and of course, I must say here that these examples have been generated using the MATLAB simulation toolbox, image processing toolbox, and if you can see, this is a image of a printed circuit board layout. It has two different gray levels, the bright and a dark one, and the histogram also says the same. Okay, so you have pixels which are very bright here, that is the probability here. Of course, the actual number of occurrences are plotted here, are provided here, and there are of course some pixels which are on the darker side somewhere here. This is the darker range and this is the brighter range. Look at this image as for example, it is a foreground white image. The previous one image had two prominent intensities. The next one has a foreground white and a considerable amount of dark pixels which accumulate here in terms of its probability or occurrence, and you can see the last vertical line here which tells that the brightest pixel, there is a huge amount of pixels which are bright all over this image. Okay. All bright pixels are occurring here. Okay. Some more examples. This is an image with more prominent dark background. The previous image was, if you remember that the previous image was a case of white background, it is a dark background. So, this is the background which is dark, okay, and the histogram also shows that there are quite a large number of pixels with darker intensity, and of course, there are a few in the brighter region as well, but quite few. Okay. These pixels corresponding to this particular region of the image. You can see here, this is an image with more or less uniform coloring except the background. So, this is a very large background which occupies a large portion of the screen, so which is occurring here in terms of the histogram, and of course, there are quite a few pixels on the brighter side, which are occurring here in the image, and their histogram shows here. So, we had seen about 4 different examples of histogram, images and their histogram, and I must also tell you that what does the histogram give you? Well, it gives you a probability plot, that it just tells you the number of occurrences of a gray level value within an image, number of occurrences of gray level value within an image. It does not tell you anything else. What is the information content? Is it the image of a face? Is it the image of a printed circuit board, or is it an image of an aerial view of a city or the sky? No, that information is not present in the histogram. I should say here, and you should keep it in mind, that the histogram gives or reflects the global appearance, not any structural information or the content information, a global appearance in terms of its quality of the image. It might tell you that, well, the image appears to be on the darker side, or it could be on the brighter side. You can look at the histogram and tell that. You can look into the histogram of an image without looking into the image and say, well, it seems that it is a very dark image. We could say that image is probably very bright, or you could also say that the dynamic range of the pixels is quite wide, that image probably is of good contrast. Okay. It may happen when you have the perfect histogram should be a flattened histogram, which we are trying to do by the process of histogram equalization now, which we will see. So, we will look at different applications of histogram now, or the use of histogram. As you say here, the histograms are simple to calculate. We have seen the formula of the histogram just now. Before we looked into the examples, it gives information about the kind of image or the global appearance and its properties. Remember, this global appearance is a very qualitative term. It does not tell you about the structure or contents of the image, whether the image is of a classroom or an outdoor scene or a photograph of a flower or a garden. No, there is absolutely no information about that in the histogram of an image. It just gives you the global appearance in terms of the lighting distribution or gray level distribution, probability distribution. That is all you have in the histogram, but you can work magics using that, and people have used histogram for many different applications, which we may not have time, but we will see how to enrich the contrast of an image or by using the histogram. So, the histograms are simple to calculate, as we see here. It gives information about the kind of the image and its properties, that means basically global appearance. It is used for image enhancement, which we will see here next. In terms of histogram equalization, it is also used for image compression, not to a great extent, but yes, it can be. The other big application is it is used for image segmentation, and it can be used for many real time image processing applications as well. We shall now look at histogram equalization, which is the main point of discussion now, and here the goal is to obtain a uniform histogram for the output image. Okay, what do you mean by uniform histogram, and how do you obtain it from by using histogram equalization? So, what is histogram equalization? Well, the method is completely automatic. Even computing the histogram and performing histogram equalization, both are completely automatic. And to perform histogram equalization, we must consider what is called the CDF, or cumulative density function or distribution function, CDF of the transformation function in this form. S equal to TR is what we need to obtain in terms of contrast stretching, and if you are using histogram equalization to do contrast stretching, this S equal to TR function must be evaluated using this integral formula. 0 to R, PR of R we know that is the histogram or the probability, W in this case is just the dummy variable for integral, and this is just the histogram here. Okay, so, that is the formula for histogram equalization. I am going over a few mathematical concepts here, keeping the equations as simple within the time limits available to us. Mathematically, the discrete form of this analog or integral equation of the transformation function for histogram equalization is given as this. Remember, the integral is a sigma in the discretized world. So, that is what this is here, as you can see, and this is nothing but the histogram nj by n. So, sk t of rk, remember that is the discrete form. K is indices, integer indices running from 0 to L minus 1, L for L different gray level values, RK normalized range 0 to 1, and SK equals T of RK is nothing but this summation, which is nothing but this, and this sigma PR of Rj, sigma 0 to j running from 0 to k, PR of Rj is nothing but this particular integral. This integral in analog form is discretized here in the discretized version of this integral, and this, if you substitute from the formula of the probability distribution or histogram, gives you this. So, remember, this is what you have to compute, summation of k plus 1 terms for sk equal to T of Rk, and that you have to compute for nj by n. So, that is the formula for histogram equalization. That is the formula for histogram equalization, and you have to basically sum the terms. We will look at an example, we will look at the algorithm steps in fact for histogram equalization first, which will help you to overall look at it using this formula, and then we will look at examples. One example, a classroom exercise to see how the calculations could be performed, and then we will see examples on images. So, the algorithm for histogram equalization, or HUK in short, is the input image is given, output is the input image after equalization. Of course, the first task is to compute the histogram H of xi of the input image itself. So, for the input image, compute the histogram, calculate normalized sum of histogram, that is another way of calling it, or it is also called the CDF, normalized sum of histogram or CDF, given by the formula earlier, and that computed CDF is nothing but your transformation function S equal to TR. So, transform input image to output image using this transformation function S equal to TR, where this S equal to TR is nothing but your computed CDF. And what was the formula for CDF? You remember, this was the formula for computing the cumulative density function or distribution function for the input image. Okay? So, that is what you have for your algorithm. So, whenever your transformation function S equal to TR is equal to the CDF of the image, okay, or what is called as the normalized sum of the histogram, then that gives you histogram equalization. That is as simple as that. Okay, easy to implement, the formulas are very easy, as you can see here, and we will start to look at an example on how to perform histogram equalization on an image. So, let us look at it as an example in discrete case. I encourage all people to work out this example in your paper as we go along. Okay, just check the values. As you can see here, Rk, there are 8 gray level values, normalized 0 to 1. So, 0, 1 by 7, 2 by 7, so on. So, there are 8 values 0, 1, 2, 3, 4, 5, 6, 7. Yeah, there are 8 values. So, k will run from 0 to 7, 8 discretized gray levels running from 0 to 1, and the gray level occurrences of value 0 are 790, 1 by 7023, and so on. And if you sum all of these up, you will get a value 4096. You can, I leave it as an exercise for you to check up that this 4096, which is the total number of gray level values, if the image is a square array, can you guess what is going to be the size of the resolution of the image? How many rows by how many columns the image will have? If the total number of pixels of gray level is 4096, it is easy for you to guess, it is 64. 64 cross 64 gives you 4096. So, after you compute the histogram, you should ensure that the summation of all these values is this particular value, total number of pixels in the image, and this is your normalized histogram, that is PR of RK. How to get this value? Divide 790 by n, nk by n, this is your n, 4096. Total number of pixels in the image. So, nk by n gives you this value. So, each of these first 8 values divide by this n, this is what you get. This is what you get of PR of RK, and you must again verify that the sum of these values, as the sum of these values gave you 4096, sum of these values should give you 1. If it is not so, if all these fractional values do not add up to 1, what is the sum of these fractional values in terms of the plot of PR of RK? If you look at the plot of PR of RK versus RK, we will see this plot later on, it is the area under that curve. That area under that curve should be equal to unity, because the sum of all probabilities, is 1. So, that is what you have here, PR of RK, sum of these values is equal to 1. So, A, which is the first column, quantized gray levels, B, the sample histogram which we have taken as an exercise, and its PDF or the histogram is given in the column C, the third column. So, let us go ahead and start the computation of the CDF for this particular example and try to equalize this image. Of course, we are not bothered about the image here itself, it could be any image for which the histogram is computed here, and we will look at the case of how to equalize the histogram. That is our main exercise. So, look at its CDF. How to compute the CDF? As you can see, I was telling you earlier in the expression, that is what you have to compute the cumulative density function, its sum of the values. So, 0.9 here, 0.9 plus 0.25 is 0.44, 0.44 plus 0.21 is 0.65, 0.65 plus 0.16 is 0.81, so on. So, at any position or row of the CDF, this a particular value will be the sum of the all the previous PR of RK values from the beginning RK equal to 0 to that particular value k, and you must also reach a value 1 at the end. Actually, if you do not reach a value 1 here, you will not reach here, or as you keep on adding this to 0.25 to 0.19 to obtain the next value, 0.21 to 0.44 to get the next value, and so on, you should also reach a value 1 at the end. If you do not reach a value 1.0 or 1.0 there, you would have definitely made a mistake in the calculation somewhere in computing this histogram or its CDF. So, that is the computed CDF value, and what is the quantized values? Here, the quantized values are given here. How to compute these quantized values? Well, you can see we are working in the discretized domain, and there in the discretized domain we do not have all the values from 0 to 1. These are the only possible values. So, we look at a fraction of one of these fractions, 1 by 7, 2 by 7, and so on, which is nearest to this decimal value 0.19, which is the closest, that is what we assign. So, that is the approximation to the nearest gray level value is in the last column E, where we have approximated this decimal value to this quantized value. So, 0.19, the nearest quantized value or fraction is 1 by 7. The nearest quantized value for 0.44, a decimal value here, is 3 by 7. 5 by 7 is the nearest fraction for 0.65, and so on, and all these will actually round off to the nearest quantized gray level value of 1. So, this is how you have not completed the histogram equalization, but this is how you compute the CDF at least. Okay, CDF in analog sense, and in discretized domain also we must actually see what is the quantized gray level values here, because CDF could appear as a continuous function after this fractional values, and none of them actually could be equal to a quantized gray level value. That is possible, but you have to do this assignment in terms of quantized steps. These are the quantized, these are different quantized steps possible of values of RK, the quantized gray level values as given here, the column A, and you have to find out any value for any value of CDF here, the decimal value, which is the closest fraction out of these 8 possible quantized gray level values, and put that value here. So, that is what is done. You can check it yourself that these will be the values from obtained from CDF. Let us go ahead and do the equalization. So, where we were in the last slide, this was the original histogram. If you remember, this we had explained in the previous slide, okay, gray level values, gray level occurrences and the probabilities, which is the histogram, the original histogram here, and this was that for an RK. Now, we have combined the previous two tables in the previous slide, and for a value of RK, CDF points to SK, which is this, and the nearest quantized gray level value is given here. So, this is the transformation function from RK to SK, which will give you the histogram equalization. So, it basically means that all well gray level values with 0 in the original image should be transformed to 1 by 7, all gray level values 1 by 7. How many of these are 1 by 7? 1023 of them. 790 pixels with gray level value 0 will be transformed to 1 by 7. 1023 pixels of gray level value 1 by 7 will be transformed to 3 by 7. 850 pixels with gray level value 2 by 7 will be transformed to 5 by 7. 656 pixels with gray level value 3 by 7 will be transformed to 6 by 7. 329 pixels with gray level value 4 by 7 will be transformed to 6 by 7, and so on. So, that is how it is done. So, that is the transformation function, and that is what we use to equalize the image. The last finally, this is the transformation function RK to S of k, and the new histogram is what you have given here. Because SK, these you can see that the transformation function may not have certain gray level values. There are no pixels with gray level value 2 by 7 or 4 by 7 as computed earlier in this table. And 790 pixels had a value 0, gray level value 0, and those have been assigned 1 by 7, and that is the probability. You should see that the sum of these values should also add up to 1. You can do that calculation right now. 0.19, 0.25, 0.21, 0.24, 0.11. Some of these 5, in fact, if the others were also non-zero, you have to add all of them, summation of these probabilities, as we have done for original histogram, for the original image, for the transformed histogram equalized image also, this summation of these values should be equal to 1, okay, equal to 1, and this is the transformed image. So, this is how you do the histogram equalization. Let us look at the plots. This was the original histogram. If you look at the plot, when we had a 0.19, 0.25 and the decaying value, okay, you can look at the values here given in the previous slide. Let us go back. Yeah, this was the table. This was the original histogram. These were the values, and this is what I am showing you in a plot in the next slide. Here, let us see. Yes, this is the plot. What do you infer from this histogram, which we are going to equalize, or we have already equalized in the table, but we will show the plot now. So, this is the PR of RK versus RK, and this, first of all, it is not equalized. This is a scope of equalization here, because histogram does not appear to be flat. There are more number of pixels with darker gray level values. The image might appear darker. So, we are trying to enhance the image by adding more and more gray level values, but we cannot do it in a random fashion. Just simply transform some of the darker gray level values to bright will not solve any purpose for you. So, we are doing it in automatic fashion using probability distributions of the histogram or the histogram and the CDF equal to the transformation function S equal to T of RK. When it is equal to CDF, that is your histogram equalization algorithm. So, let us look at the cumulative density function of this image. Okay, let us see how it looks like. Okay, that is the plot. So, any typical CDF of an image will look like this. Of course, the nature by which the curve, the points of the curve go up will vary from one image to another, okay, but it will monotonically keep increasing all the time. That is a property which is used or exploited to perform histogram equalization. So, the values go up, and this is the constructed from this histogram, and we know how to do that. This table of values is also given in a couple of slides back, and that is your CDF of the image of the transformation function used for histogram equalization. And when you do that, this is the new histogram. As you can see here, some of the values have disappeared. There are no gray level values, no pixels with gray level values 0, 2 and 4, but you can see this is much flatter compared to the histogram, which has a very exponential decaying nature here. Large number of pixels dark, hardly any pixels in the bright. Now, you have quite an average distribution, which where there are quite definitely there are pixels in the darker range and some in the brighter range. So, that is the histogram equalization example. Well, I am sure there are lots of questions which come into your mind. The first question is, do you gain anything, and really do you think that the histogram is equalized or it has flattened out? Well, it has, but it does not appear so neat and nice. Well, that is due to the discretized nature of the data. It is due to the finite number of gray level values we have, finite number of pixels we have in the image. When we move out from the analog domain, the equation to the discretized domain, and we are doing a lot of rounding of operations, so some pixels might disappear, and actually some pixels may be reintroduced. It may happen in the discretized domain that some pixels may be reintroduced back, which may be absent in the original histogram. So, that is possible in histogram equalization, and that is why, but the plot of the equalized histogram which you see is not truly flat, and some pixels are missing because due to two principal reasons, that we have considered a very small image with a finite number of gray levels and pixels. The more larger resolution of the image you have, more larger number of gray levels you have, practically if possible, it is not possible, hypothetically if it is both are infinity or as large as a possible value you can imagine, then only you will have an absolutely flattened histogram with all gray levels possible. So, that is the reason why you see that the new histogram here appears to be quite flat, but it is not flat. Definitely it is much more flatter than the original histogram, and of course some pixels are missing. Let us look at some examples. This is a very neater example. As you can see, this image is not that rich in contrast. This is the original histogram of the image, or histogram of the original image, and there are no pixels on the darker and brighter side. You first equalize in this range, and then this is the output after transformation, which you see that this is much richer in contrast than this particular one. Let us look at another example. This is an image of the city of Venice, and this is an histogram. Well, it is not flattened, but you do have dynamic range of pixels from dark to very bright ones, except the very bright ones are absent in this, but it is not flattened. So, when you try to flatten this, the histogram will appear something like that. As you can imagine here, that it is flattered, but not absolutely flat, but of course, and one or two pixels may be missing as well, and when you try to flatten this, the output image will appear something. Well, if you observe very carefully, there is a little bit of enhancement. There are some very dark regions which have become a little bit brighter here. Some details which are very dark around these regions, or even the water body, as you can see here. The Venice Palace is on the back side. It is a city submerged in water mostly, and the foreground here, very dark regions have little bit become brighter, including the water body. So, that is the change which one can make. This image is quite good in quality, it is not that bad. So, this histogram equalization tries to do its best, but it is not always good. We will see an example here. That is a very good quality image, because it is used for all examples starting from image compression, segmentation, enhancement. You do not need to enhance this image, but if you try to enhance this image, you can almost imagine what is going to happen. This is the example of the histogram. It is not flat, but it is quite broad spectrum histogram, in the sense that there is a lot of dynamic range of pixels present here, and you flatten it out, this is the output which you have. Well, there is hardly any difference. In fact, it has worsened the quality somewhat, if you carefully observe that this image is saturated somewhat. Okay, so, sometimes do not try to perform a histogram equalization on an image which is quite rich in quality by itself. Another example where histogram equalization should be avoided. Okay. So, that is the case of examples we have seen about histogram equalization, and we will move to the last section of this lecture, where we will talk about noise removal or smoothing, using smoothing operations in an image. So, let us look at smoothing in spatial domain. The simplest approach is what is called the neighborhood averaging, where each pixel is replaced by the average value of pixels contained in some neighborhood about it, and the simplest case is probably to consider the group of pixels centered on the given pixel, and to replace the central pixel value by the unweighted average of these. When you talk of weighted, we can use a Gaussian mask or a Gaussian function, but it is unweighted average of 9 pixels in a 3x3 neighborhood. Let us look at an example of what this means. Okay. For example, the central pixel in this figure given below is the value 13, that is the nearest integer to the average. If you take all these 9 pixels in a 3x3 template or window or mask, as it is called, average of these 9 values, 3x3, 9 values here, will give you 13. As you can see in this image, it appears that this value should have been 13, or somewhere near to 10 and 11, or lesser than 15 or 14, but this is probably due to a noise effect of noise which has caused this pixel to shoot up well above its values around it. So, you can average it and replace it by a value, in this case it works. So, if any one of the pixels in the neighborhood has a large or a faulty value due to noise, this fault will now be smeared over all the 9 pixels as the image is smooth. This tends to blur the image. That means, this value will not only affect this pixel, but all these other pixels when you do averaging around the image, all the neighborhood pixels also will be affected. Of course, if this is a case of 3 by 3, you can average using 5 cross 5 or 7 cross 7 window, the effect of blurring will be still larger. The effect of blurring will be still larger. Let us look at a different type of a noise, which is called a spike noise here. Let us say this pixel is, the central pixel is replaced by 13, that was noisy in the previous case as 23, so that I replaced with the original value, let us say, and the pixel on the left which had a value 11, I put a large amount of what is called a spike noise. That means, this is so large compared to its neighborhood that is definitely it's something like an impulse or a large spike which has come. So, it is called a spike noise. So, average value of the central pixel, if you see, it gets corrupted. It is a value 23 which you get as an average. So, it corrupts not only this, but if you try to compute the average around here, anywhere surrounding this spike noise, it will affect all the neighborhood. So, the averaging effect or the effect of averaging using spatial domain, effect of smoothing using spatial domain averaging is not a very good method to remove noise. It works to a certain extent, but it does not work beyond a certain point, and especially it is very worse in the case of spike noises. Okay. So, better approach is to use a median filter where a similar neighborhood around the pixel under consideration is used, but this time the pixel value is replaced by the median pixel value in the neighborhood. Okay. So, instead of, we are proposing a technique of median filtering which is also very popularly used. So, instead of spatial averaging where we took a set of pixels around the neighborhood and computed a simple average, and we know the problem using averaging now, it is a very common simple technique, averaging can be used. We replace it by a concept called median filtering. So, we will understand what is this concept of median filtering now. Okay. Thus, if we have a 3 cross 3 neighborhood, we write the 9 pixel values in sorted order. So, what is the method of median filtering? We are discussing the concept of median filtering where I read again that if we have a 3 cross 3 neighborhood, we write the 9 pixels in sorted order and replace the central pixel by the 5th highest value. Well, I am taking a 3 cross 3 neighborhood and that is why I have 9 values, but nobody stops you from taking a large neighborhood. You can have 5 cross 5, then you have 25 values which you need to either average in case of averaging, or when you are doing median filtering you need to sort those 25 values, and the median in that case for 25 values will be the 13th value. In the case of 3 cross 3 neighborhood, when you have 9 values, the median is the 5th value, we have seen that. In the case of a 5 cross 5 neighborhood, when you have 25 values, the median value is the, which is the median value? The 13th one. If you choose a larger window, 7 cross 7 let us say, you can start guessing why I am talking about odd numbers, not even 4 cross 4, 6 cross 6, that is easy to guess. I will leave it for you to think. 7 by 7, 49 grade level values, what is the median? 25th one. Good. So, but for simplicity here, in order to handle the values in this screen, we are talking of simply 9 pixel values, and you replace the central pixel by the 5th value only. So, for example, again taking the data shown in the previous figure, the central pixel value is replaced by 12. So, if you have sorted values like this, what is the median value? First, second, third, fourth and fifth. This is the median value. So, you just do not worry about the median value is the 12 here, which is highlighted and underlined here. So, as you see here from the previous template, the 3 cross 3 neighborhood gives you 9 pixel values, then you need to sort them. When you sort them, as you see in the spike noise, if it is a low spike noise, a low value, or even a large value here, the spike noise will be shifted to the end of that sorted order. It will be either at the beginning or the end, depending upon whether you have a small or a large value. Take the median, you will be safe that is going to be close to the actual true value of the set of pixels. Okay, so, that is what is median filtering. Take the neighborhood, sort all of them, select the median value, that is simple, and you can do it all over the image and it works reasonably fairly well, definitely much more well than the neighborhood averaging. So, the approach has 2 advantages as we see here in the next slide. Occasional spurious high or low values are not averaged in, they are ignored. That means, spike noise is thrown out. These Spike noise causes occasional spurious high or low values of gray levels, and those are not averaged in. The spurious spike noise with a very large or small value will affect the average value. That is what it was doing, and also it will start spreading and cause an effect which is called blurring in the image. Larger the mask, from 3 by 3 to 5 by 5, 7 by 7, or even higher, 11 cross 11, or even 23 by 23, or even larger. If you visualize, the more larger window size you take to operate the neighborhood averaging, more the effect of blurring, but the median filtering does not have that. Median filtering does not have. You can take an even larger size, and if the larger size window captures 2 or 3 different spike noise pixels having 2 or 3 different spike noise at 2 or 3 different places, since you are shorting them, those values will be the extreme end at the beginning or the end of the array of the shorted sequence, and you pick up the median value. So that is what I say is that the occasional spurious high or low values are not averaged in, and they are ignored. And the other important advantage is the sharpness of edge is preserved in this. And to see an example, let us consider the pixel data as shown below, which will say or illustrate what you mean by sharpness of an edge. This is an edge where you see that the pixel value to the left of an edge, I am drawing the edge in the vertical direction here, are certain constant values here, to the right they are different, and I want to preserve. Now if you can imagine here, if I do a 3 by 3 averaging around these pixels here, this 10 value will go up, 20 value will go down, bringing the sharpness of the edge will disappear. Okay, the sharpness of the edge will not exist anymore, and to preserve that, what the median filtering will do, when the neighborhood covers the left hand 9 pixels, the median value is 10 anywhere here, and when it covers the right hand ones, the median value is 20, and hence the edge is preserved. You can take any central pixel, take a 3 cross 3 neighborhood, suppose this is the pixel you are considering, the value 20, and you take a 3 cross 3, short these values, take the median, you will have a value 20 here. Let us take this pixel, you take a 3 cross 3 set of pixels here, replace it by the median one, you will have a value 10 here. So that is what we are reading here. So when the neighborhood covers the left hand 9 pixels, which is these 3, you have the median value 10. When it covers the right hand ones, that means this set of 9 pixels 3 cross 3 are covered, the median value is 20, which will be replaced here, and hence the edge is preserved. So it is two important properties, advantages of median filtering. It preserves edges and it removes the spurious noise. Few information about noise. If there are large amounts of noise in an image, more than one pass of median filtering may be useful to further reduce the noise. You can use such a concept. And a rather different real space technique, we are not talking of any spectral domain techniques here, for smoothing is to average multiple copies of the image. Where do you have multiple copies? Well, if you are talking of a video where the frames, inter-frame differences are not much, you can actually or there is hardly any movement or negligible movement, or in fact if possible no movement, static phase video taken, and you have lots of samples, few tens or few hundreds of them, and even if there is noise, you can actually average it out across time frame to get a better image frame which is noise, free of noise. So that is what is talked about here. Average of multiple copies can be done. The idea is that over several images the noise will tend to cancel itself out if it is independent from one image to the next, and statistically we expect the effects of noise to be reduced by a factor of root over n. Okay, I am sorry, it is 1 by root over n if we use n images. For particular situation where this technique is of use is in low lighting conditions. So let us look at an example of median filtering and compare that in the time remaining to us with the averaging technique. Okay, so we have seen two types of techniques now of removing noise. One is averaging, which we know is not that powerful, especially with respect to spike noise. It degrades the sharpness of an edge, it is unable to handle spike noises, and we have seen median filtering, which is powerful. So let us look at the original image Lena again, and I have corrupted this image by adding noise. You can see that the image is quite noisy compared to the image which is very clean here. Absolutely, this is the original image. I have just corrupted. You can do that using any simulation toolbox. I have used the MATLAB simulator to do that, very simple, and I apply the median filtered image. You can see that the median filtered image is quite close to the original image. In fact, it is much better in fact than with respect to the noisy image. Let us look at another example of an original image. This is the noise image. In fact, this is the spike noise. The previous case was a salt and pepper noise. This is the spike noise here, and these spikes you can see can be removed by median filtering. There is a little bit of defocusing or blurring effect all right, but the median filtered image is much better than the noisy image, and in fact it is quite close to the original image. So, these are examples of methods by which you can filter an image, and of course you can, I leave this exercise for you, you can use any simulation toolbox or write a program yourself, read an image in bitmap form, then try to remove the noise by average filtering, then try median filtering and see which one is better. I can almost guarantee you that in most situations the median filtering will win. Of course, there are many sophisticated techniques which are even better than median filtering, but we have no scope of that in this course. We have to look for techniques based in courses like digital image processing, which we will discuss more of these aspects here. But when you need to just clean off an image for use in computer graphics applications, for image based rendering or image based or want to map an image onto a certain background, it is better that you clean it if necessary, if there is noise in the image. Okay. So, that completes our discussion on image filtering or image enhancement. We have discussed firstly the contrast. First we have discussed contrast stretching, okay. Then by transforming the gray levels, then we discussed at length today what is histogram and histogram equalization based method, and then of course noise filtering by smoothing and median filtering. I would like you to look and note down the references which I used for this particular part of the lecture, and this is also applicable for JPEG compression. And the book, recent book by Gonzalez and Vince has a chapter on image compression. I would encourage you to read that, and these are the list of references about digital image processing. So, that brings us to the end of the lecture series on computer graphics as well as image processing. So, today we wind up digital image processing, compression and enhancement are the two aspects we discussed in the last two lectures. In the last lecture it was compression, it was enhancement in this lecture, and that brings us to the end of the entire series of lectures in computer graphics. I hope you have enjoyed all the lectures, understood, but I encourage you to go back, read books, the references which are given for both computer graphics and the last two lectures on image processing, and then try to write some programs, maybe using OpenGL, which we had a lecture on that as well, couple of lectures on OpenGL, and try programming. Of course, you can use some simulation toolboxes for graphics using VTKs, okay, virtual reality toolkits you can use, but I will ask you to do programming as computer science engineers and scientists and experience the real world of computer graphics and also virtual reality. Thank you very much.